Good morning, everyone. My name is Shivam Gupta, and I have done my capstone project under Dr. Alpana Agarwal. It's a research-based capstone with main focus on implementing improved testing algorithms for mixed signal circuits, mainly phase-lock loops and analog to digital converters. So this is the flowchart of the project. First of all, the dataset is taken for the phase lock loops, and then a suitable algorithm is used in the MATLAB to calculate the phase noise and jitter at the output of the phase lock loop. And then the plots are drawn in the MATLAB. The next part is to calculate the static parameters of the 6-bit ADC, flash type ADC. So I've used histogram testing to calculate the INL and DNL errors of the ADC, and then draw the certain plots in the MATLAB. So first of all, what are the mixed signal circuits? Mixed signal circuits can be defined as integrated circuits which consist of the both digital and analog elements on the same chip. And the most common circuits that we use are analog to digital converters and digital to analog converters. And another common mixed signal circuits are phase lock loops. So what are phase lock loops? A PLL is tracking a phase lock loop is a tracking circuit that synchronizes an output signal generated by an oscillator. And a phase log loop attempts to maintain a constant phase and frequency between the input signal and the voltage current driven oscillator. This is a circuit diagram of a phase log loop. And then what are the analog to digital converters? We use analog to digital converters to convert the normal real analog signals to digital signals. And what are the process in the conversion is, first of all, our circuit is sample, the input signal is sample and hold. Then this signal is quantized, and then a certain encoding is done to convert it into the digital signal. It translates analog signals, real signals to digital signals. So this is the whole process of the ADC conversion. And we have used flash type ADCs. Flash type ADC is based on the principle of comparing analog input voltage with a set of reference voltages. It is the fastest type of ADC because the conversion is performed simultaneously through a set of comparators. The construction is simple and easy to design. So this is an example of a 2-bit flash type ADC. Now, what are the static converter errors? That is our main focus to calculate the static converter errors. The number one is differential nonlinearity. It is the maximum and minimum difference in the step width between the actual transfer function and the preferred transfer function. Nonlinearity produces quantization steps with varying widths, some narrower and some wider. For the case of the ideal ADC, the step width should be 1 LSB, least significant bit of that ADC. The step width of a non-ideal ADC with DNL are not exactly 1 LSB. It is greater or smaller than the 1 LSB. The second static converter error is integral nonlinearity. Annual error is described as the deviation in LSB or percent of full scale range of an actual transfer function from a straight line. Nonlinearity produces quantization steps with varying widths, some narrower and some wider. So what are the testing techniques used to measure static errors? The technique I have used is histogram testing. So what is histogram testing is, we have taken the ADC output, and then we have taken a 6-bit ADC and given an analog input signal. The histogram shows how many times each different digital code word appears on the ADC output. The digitized information is then sorted into code bins. Each code bin represents a single output code. Depending on the input signal, the number of samples or hits for each bin is collected, with n representing the ADC resolution or total number of bits. In our case, n is 6. So we have 2 raised to power n code bins. So total 64 code bins. So depending on the input signal, the number of samples or hits of each is calculated. For instance, if the number of collected samples in a code bin is greater than expected, then this number would be indicate that the code bin width is larger than ideal. So now, how to extract the DNL and INL from the histograms we get? So first of all, we remove the overrange bins, first bin and the last 0 and full scale. Then we compute the average of the number of counts of each count of samples in each bin. Then we normalize, divide histogram by average count by bin, and ideal bins have exactly the average count, which after normalization would be 1. So which means DNL error is 0. But non-ideal bins would have a normalized value greater than or smaller than 1, which means there is some DNL error present. So subtract 1 from the normalized code count. Result is a DNL error, which can be negative or which can be positive. depending the width is smaller or greater than the 1 LSB. And the integral nonlinearity is just the cumulative sum of the DNL. To calculate the INL, we just summation, do the summation up to that point of all the DNLs up to that point. So measuring INL DNL using MATLAB, we just give the ramp signal as the input with the maximum voltage swing of 1.8 volt, varying from 0 to 1.8 volt. The output of the converter is this, and we uh, and the number of codes coming out to be 57, which means there are some codes absent, because ideally for 6-bit ADC, the number of code bins should be 64, but we get 57 codes. So 7 codes are absent. So this is the DNL INL plot. As we see, DNL and DNL can be negative or positive, which means DNL is present, and the maximum DNL error found to is 0.4 LSB, positive and negative, and the maximum INL present is 1.4 LSB, which is the cumulative sum of the DNL. IEEE standards used in my project is IEEE standard 124121 2010, which is the IEEE standard for terminology and test methods for analog to digital converters. And the next IEEE standard used is the IEEE standard 1241, that the benefits and risk of ADC histogram testing. Thank you.